Based on the calculations that we have done, now we can create the model of the blade using CAD software. We can use any CAD software with 3D modeling capabilities. Most of them have similar basic commands to build the 3D model. First, we built the core of the blade, which is a sphere of diameter equal to the width of the blade, W. Next, we split the sphere into top and bottom parts. This is done by cutting the bottom part of the sphere and then replicating it by mirroring. Subsequently, we flatten the top and bottom parts of the core by scaling it down to 40% of its original thickness. Now, we extend the top part of the blade's core to obtain the required length L of the blade. As you can see, we have the structure of the blade with the required blade aspect ratio L per W. Next, we build the pole to attach the blade into the axial. To obtain the curvature of blade airfoil, we cut the blade's core with its clone. Note that the clone is shifted to the left side. After cutting, we have the blade structure with airfoil curvature. Lastly, we add the insert feature to lock the blade in the axial slot. Finally, we have the blade model with the airfoil curvature. The airfoil curvature is used to capture wind efficiently. This curvature shape and dimension dictates the aerodynamic of the blade. It determines and controls the front wind velocity. Now, we are ready to develop the blade using the 3D printing. There are a few details that are added to the axial and blade structures. First, the axial has 3 slots to adjust the angle of attack to be 0 degrees, 45 degrees, and 90 degrees. Second, the pole of the blade has an insert feature to lock the blade into the axial slot. Next, we are ready to test the blade. Now, we are ready to test the blade's performance. We will show you a simple experiment to obtain how much torque the blade can generate. We will measure the generated power in watt and blade rotation in RPM under different set of wind speed. Then, we can obtain the generated torque with the simple formula. Torque is equal to power divided by RPM times 30 over pi. Under wind speed of 3 to 3.5 meters per second, the tested torque is obtained equal to 0.025 to 0.026 Newton-meter. On another hand, the calculated torque in our design equation is equal to 0.072 Newton-meter when wind speed is equal to 3 meters per second. So, the calculated torque is much higher than the actual tested torque. This is because we do not include the mechanical loss, friction loss, and electromagnetic loss in our calculation. Next, we will evaluate the actual torque for different blade angle of attack. In this experiment, we can set the angle of attack into 3 values: 0 degrees, 45 degrees, and 90 degrees. When angle of attack is equal to 0 degrees, the difference between front wind and back wind velocity is close to 0. As the consequences, the torque is equal to 0. As we can see here, there is no rotation in the blade because the torque is equal to 0 regardless the wind speed. On another hand, when angle of attack is 90 degrees, the front wind velocity is equal to 0. This also led to 0 torque value. We can also observe that there is no blade rotation because the torque value is equal to 0. Then why do we need to have the angle of attack option as 0 degrees or 90 degrees? This option is very useful during maintenance of the wind turbine. Ideally, we want the turbine to be idle for safety during maintenance. Zero torque option is also useful during high wind condition that can damage the blade and generator due to excessive force being applied to the blade.
In the next video, we will share the optimization method to improve the generated torque by the blade. And we also share how we apply the Balinese local wisdom in kite making for wind turbine application. If you like what we do, Please support us by subscribing to this channel. Remember, don't wait for what the future inherits us, because we can change the world today. Thank you for watching. See you!